thank you for being here, in spite of the heat, or maybe because of the heat, the air conditioning here. So I'm going to talk about flexoelectricity, and it is, I guess, a sign of how times have changed. That there are now sessions dedicated to flexoelectricity. It's its own independent subject. When I started working on flexoelectricity, it was a very solitary endeavor, to the point that when I had to justify working on flexoelectricity for the ERC grant, I went to the interview and the guys asked me, so if you think this is going to be so cool, why is nobody else doing it? And that's literally, they asked me that question. They actually didn't give me the grant for the first time. Now, hopefully, I don't need to justify that it's cool, but hopefully you will see it's a useful thing to do. Okay. It's going to be a long talk because it's 90 minutes. I'll start with the things that you need to know for sure, which are the basic properties, the physics of flexoelectricity. You should also know how big is the effect. And this, you don't need to know, but it might inspire you. So when we get to the applications and manifestations of flexoelectricity, we'll do as many as we have time to do. But if I don't have time to do everything, we can discuss it. Okay. Now, before I even start talking about flexoelectricity, I need to remind you of something that is quite important, and it will become apparent why it's so important, which is which has to do with the nature of ferroelectricity, and more specifically of perovskite ferroelectricity. Remember, perovskites come from a high symmetry phase that is cubic and centrosymmetric. So when they become ferroelectric, the up state and the down state have the same energy, and they have the same elastic energy. The up unit cell and the down unit cell have exactly the same shape and exactly the same size. Which means that by pressure, I cannot go from an up state to a down state, because there's no energy gain. Okay? If I apply pressure, I can change the magnitude of the polarization, but I cannot change the sign of the polarization. Okay? That's quite important. Okay, right, that's before we start, now we start. So what is flexoelectricity? Flexoelectricity is a dielectric polarization induced by a strain gradient. Strain gradient is a difference in strain. And I always use this figure to illustrate it. You can start with a perfectly centrosymmetric unit cell. And if you apply some compression at the bottom and some extension at the top, now you have a strain difference, which divided by the size of the unit cell will be the strain gradient. And it may happen that when you do that, because there's now more space available at the top of the unit cell, this cation here may want to move up, thereby giving you some polarization. So that's a bit of a cartoon image of what happens, why is it possible to get polarization just from strain gradients, even in unit cells that are centrosymmetric to start with. Okay? And if you want to think of it in another way, it's a bit like squeezing the toothpaste out of the toothpaste tube, right? You squeeze the bottom, toothpaste comes up. That's more or less what happens. Okay, so this is a cartoon picture. This is the more exact mathematical definition, the polarization given to you by a strain gradient. Strain is, it's a two-rank tensor. The gradient turns this into a third-rank tensor, which means that this is an odd parity tensor. That means that the strain gradient by itself breaks centrosymmetry. Okay, it's an odd parity tensor. This, which means that the flexoelectric tensor can be even parity. It's a fourth-rank tensor, which means that it's allowed by symmetry in pretty much any material. Okay, you are not limited to non-centrosymmetric materials. If you remember, piezoelectricity is only possible in materials that have an asymmetric unit cell. Here you can start with a symmetric unit cell. The flexoelectric tensor allows you to do so because the strain gradient itself, the deformation itself, is what breaks the symmetry. Okay? And as so many things, this was first proposed in the Soviet Union many, many decades ago. Okay? That's a theme that emerges. So Michel Viret said the other day something that is almost a gospel, which is that good enough is always right. There's another commandment, which is that whatever you do, the Russians did it 50 years ago. And that's the way it works. Okay, so just to emphasize again this thing because it's quite important, if you start with the centrosymmetric unit cell and you apply a homogeneous deformation, which is by definition a symmetric deformation, so you apply the same force from either side, you either compress from the sides or you extend from the top and the bottom, you will of course change the shape of the unit cell, but you will not break the symmetry. Okay, it was symmetric to start with, the forces that you're applying are also symmetric, therefore the end result must be symmetric. Okay, so you have something symmetric and you apply symmetric pair of forces, you will not get polarization. If you take the same unit cell but you apply an asymmetric deformation, then you do get polarization. And that's all it is. Okay? So the basic principle, the fundamental trick of flexoelectricity is that it exploits the difference between a strain gradient and a strain. Yeah? That's kind of the symmetry principle as to how you measure the two things, piezoelectricity versus flexoelectricity. Well, it's quite simple. If you have a piezoelectric material, something that is asymmetric to start with at the lattice level, then you just apply a homogeneous deformation and you will get a polarization. Okay? And the amount of polarization will be given to you by the piezoelectric tension. If you want to measure flexoelectricity, what you do instead is, instead of applying a homogeneous compression, you can apply, for example, a bending. A bending will give you compression on the concave side and extension on the convex side. Okay, so when this is pointing down, this side is compressed, this side is extended, so you will have broken the symmetry just by bending. Yeah? Okay. Someone this morning asked me about electrostriction. I'm not going to discuss electrostriction, but I should mention it. So another property, another electromechanical property that is allowed by symmetry in all materials is electrostriction, which is a strain proportional to the square of the polarization. And again, you can start with something that is centrosymmetric, you apply an electric field, the electric field breaks the symmetry and gives you a polarization, and then you get a strain that is proportional to the square of this polarization. I don't really mention it because it's not a comparable magnitude to these other two, in the sense that there isn't a reverse of electrostriction. So if I apply an electric field to an electrostrictive material, it will stretch. But if I take this material and I compress it, I will not get a polarization. And this is because the material is centrosymmetric to start with, remember, and if I apply the deformation, the polarization doesn't know in which way to go, so the polarization does not even appear. Yeah? Is that more or less clear? Do interrupt me at any point that you feel like you're getting lost. Yeah? Okay. So I just mentioned, unlike electrostriction, piezoelectricity and flexoelectricity do have the inverse effect. So in the same way that if I bend something, it will give me a polarization. If I try to polarize something, if I apply voltage to something, it will try to bend. Now how much it manages to bend will depend completely on the thickness of your sample. If you have a very thick slab and you apply a voltage, it will try to bend, but it won't manage. But if it's sufficiently thin, it will bend. Okay? If I this inverse flexoelectric effect, the radius of curvature as a function of voltage goes as the inverse of the cube of the thickness. That means that every time you halve the thickness of your sample, the induced bending that you can achieve is 8 times more, so almost an order of magnitude more. Conversely, every time the thickness doubles, the effect is 10 times smaller, which means, for practical purposes, if you take a strontium titanate single crystal and you put 2 electrodes and you apply 100 volts to it, it will bend, but the radius of bending is more or less comparable to the radius of the Earth. It's difficult to see that, right? So you're not going to see it, and that's why people haven't seen it. But if you take the same strontium titanate and you make it 100 nanometers thick, then it will bend by several tens or even hundreds of nanometers, and you will be able to see it with the right equipment, of course. And interestingly enough, inverse flexoelectricity was the very first experimental demonstration of flexoelectricity. So inverse flexoelectricity was observed before direct flexoelectricity. And of course it was in the Soviet Union. The principle still stands. Okay, I've talked about direct flexoelectricity, so a strain gradient gives you a polarization. Inverse flexoelectricity, a polarization gives you a strain gradient, so you polarize something and it bends. And there's also something called converse flexoelectricity, which is that a polarization gradient gives you a strain. It can be proven, but I can't because I'm not smart enough, that in fact inverse flexoelectricity and converse flexoelectricity are two manifestations of exactly the same thing. But even though they are essentially the same thing, experimentally they have quite different consequences. So if you want to measure inverse flexoelectricity, as you say, you apply a voltage and that will induce strain gradient, something will bend. Okay. Converse flexoelectricity, you try to apply not a homogeneous polarization, but a polarization gradient, which you can achieve by applying an electric field gradient. So if you have an electric field that is not homogeneous in your sample, that will induce a deformation that is linearly proportional to this polarization gradient. And this effect actually is quite important. You're going to have a talk about PFM, I expect, next week by Celine, and hopefully she's going to tell you about artifacts that can happen in PFM, piezo response force microscopy. I would like to mention this one because it's one that will always, absolutely always be present. If you have a PFM, for those of you who don't know this, piezo response force microscopy, basically you have an atomic force microscope, the metallic tip that you put in contact with your material, and you want to determine whether that material is piezoelectric or not. So what you do is you apply a voltage to your tip. This voltage is sensed by your material, and your material will stretch or not if it's piezoelectric. And you think that if it's not piezoelectric, it's not going to deform. However, the electric field that you're applying is not homogeneous. It's kind of more or less radially decreasing as you move away from the tip. So if you have an inhomogeneous electric field, you are going to induce an inhomogeneous polarization, so a polarization gradient, and that's going to give you a strain. So when you divide this strain by the voltage that you apply to the tip, you're going to measure an effective piezoelectric coefficient, but it has nothing to do with piezoelectricity, it's pure flexoelectricity. So as they say, if you're a nail, no, if you're a hammer, everything looks like a nail. If you're a PFM, everything looks piezoelectric. Okay, so never use just PFM to determine whether something is piezoelectric or not.
So does the polarization gradient induce a homogeneous strain, or is there also a strain gradient?
Well, okay, so the definition is a linear polarization gradient will give you a homogeneous strain. However, the polarization gradient is never linear. In this case, it's radially decreasing. So yeah, the strain itself will not be perfectly homogeneous.
Then you realize how could you differentiate the inverse and converse one?
How do you differentiate between inverse and converse? As I say, I think when you actually treat them theoretically, they boil down to the same thing. Physically, it's different. Here, I apply a homogeneous strain. So you take a parallel plate capacitor, your STO substrate, and you apply a homogeneous electric field, and then you get, as a result, a strain gradient, as in, the crystal will bend. Here, the polarization is not homogeneous, the polarization is inhomogeneous, so I have a polarization gradient, and that gives me a linear deformation. Okay, in the mathematically a linear deformation, but of course, because there's a gradient of polarization gradient, there's also, the deformation here is not homogeneous, but hopefully you can see that the physical manifestation is quite different. Okay, so here I have a homogeneous electric field gives me bending. Here I have an inhomogeneous electric field gives me strain. Yeah? In fact, the first time that this was measured was by making truncated pyramids that had more or less a linear shape. They applied the voltage between the two things, and the electric field was distributed linearly on the pyramid, and that would make the whole pyramid stretch or compress. You will see that that's also the way in which normal flexoelectricity can be used. Right, so as an example of what I'm just saying, if you look at strontium tightness and you try to measure PFM on the surface of strontium tightness, you will see a very measurable piezoelectric coefficient. I mean, this is sizable, the order of about 10, a few units or tens of picometers per volt, which is bigger than the piezoelectric coefficient of quartz. So I mean, it's not negligible. That's SPO. We've also tried this with titanium dioxide, rutile, perfectly sensorosymmetric, and you also see a flexoelectric, a piezoelectric-like coefficient that is given by converse flexoelectricity. Yeah? Okay. Now, how do you normally, or how do we normally measure flexoelectricity? Is, well, very simply, you bend something and you measure the polarization induced by the bend. It's easier to say than to do. In our case, the bending is done by something called a DMA, Dynamic Mechanical Analyzer. This is basically something that applies a periodic force to whatever your sample is. If you put your sample in a kind of 3-point bending geometry, when you apply your periodic force, you get a periodic bending. If your sample has electrodes and you connect those electrodes to a lock-in, then you can measure the displacement current. Remember, every time you change polarization, you get a displacement current, and that's what we measure. We measure the displacement current induced by the bending. And you can place the whole thing, so in our DMA we can do measurements as a function of temperature. Yes, that's direct flexoelectricity. Inverse flexoelectricity is you apply a voltage and something bends. So what we do is we take our parallel plate capacitor, we apply a voltage, and we measure the deformation by whichever means you have. In our case, we have an interferometric microscope or a holographic microscope. This is something that basically, instead of taking photos, it takes holograms. It is in 3D. And the third dimension, the vertical dimension, the resolution is interferometric, which means that it's much better than the wavelength. Whereas the lateral resolution is, half micron, the vertical resolution can be nanometric. You can also do this kind of experiment by Doppler vibrometry, for example. Okay. And so, if you take, for example, variant tight and you try to measure its flexoelectricity, you can do so by the direct method. You bend it and you measure the polarization induced by the bending. Or you can do the inverse experiment, the one that historically was done earlier. You apply a voltage, you measure the bending, and you see the bending as a function of applied voltage. And you can see that the two things look exactly the same, which is reassuring. And you can see a couple more notable features. You're probably familiar with the dielectric constant of variant tight, and if you are familiar with that, you will see immediately that the shape of the flexoelectric coefficient looks exactly the same as the shape of the dielectric constant. Okay? So that brings me to the second important feature of flexoelectricity. The first, of course, is that it's, well, it happened the wrong way around. The first is that it's possible even in centrosymmetric materials. In the case of BTO, you see that it still exists in the paraelectric cubic phase, right? So here, BTO is cubic and paraelectric, but it's still flexoelectric. Point one. Point two, it's proportional to the dielectric constant. And because it is proportional to the dielectric constant, flexoelectricity would be most important in ferroelectric materials. Okay? Everything can be flexoelectric, but ferroelectrics are more flexoelectric, right? Like animal farm. Right. Just to emphasize it, it does exist even in materials that are not ferroelectric, so you can take SPO and bend it, and if you look at the flexoelectric current, this is the displacement current as a function of bending, you see that it exists, point one, and point two, that is proportional to the capacitance, i.e. to the dielectric constant. And you can do the same, have done the same with rutile titanium dioxide. Yeah? So hopefully I convinced you that it does exist in centrosymmetric materials. It's a properly universal effect. In fact, it's even more universal than what you might think, because it doesn't just exist in all dielectrics, more or less irrespective of symmetry, but it also exists in semiconductors. And I will explain later why you can get flexoelectricity in a semiconductor, because it's not trivial, it's not exactly the same as standard flexoelectricity. And it's also very universal in the sense that it exists in all ceramics, in all dielectrics, in all semiconductors. It also exists in biomaterials, including your very own bones. Okay, well, I haven't measured human bones, but I assume that they are not going to be very different from pig bones, which is what we measured here. And as a function of strain gradient, you get a polarization. And that polarization is due to flexoelectricity, not to piezoelectricity. So bones do have collagen, which is piezoelectric, but if you get rid of all the collagen, you make the pure bone china ceramic, so pure hydroxyapatite, which is centrosymmetric, not piezoelectric, you still get the same bending-induced polarization. Okay? So flexoelectricity exists inside you. which is kind of cool, right? Right. Okay, so the two features, so far it's proportional to the dielectric constant and it's very universal. And the third very important feature is that it's inversely proportional to size. I need to explain this a little bit better. Okay, so the flexoelectric polarization is the flexoelectric coefficient times the strain gradient. Now, the flexoelectric coefficient more or less is size independent. It's a constant. Should be a constant. Like it's a tensor. But the strain gradient is not. Strain gradient is a strain divided by, well, it's a difference in strain divided by a relaxation length, right? Essentially, this differential, you can approximate it as a difference in strain divided by a difference in position. Yeah? Since the difference in position or the relaxation length is in the denominator, the smaller you make this, the bigger the strain gradient is going to be. Okay? So if you try to bend a ceramic, typically the amount of, if you try to make a deformation in a ceramic, typically the maximum deformation that the ceramic can withstand before it breaks catastrophically is of the order of, say, about 1%. Now this 1% maximum deformation that you can get, if you divide it over a relaxation length, which is between 1 and 1,000 nanometers, okay, definition of nanoscale, it gives you a number between 10 to the 4 and 10 to the 7. Which means that this number, now multiplied by the flexoelectric coefficient, is going to be much, much bigger than if you had been working at the macro scale, where this, instead of being between 1 and 1,000, it would be 0.001 nanometers, right? You can see that by going from the macro scale to the nanoscale, you multiply the maximum strain gradient that you can get by factors of thousands or even millions. Or, if you want to picture it physically, if you try to bend wood, a wood table, a piece of wood, you will not be able to bend it much. If you take a piece of paper, which is exactly the same material, it's the same cellulose thing, you will be able to bend it a lot. And since flexoelectricity is proportional to bending, you get a lot of flexoelectricity. So, it's not that the flexoelectric coefficient grows as you go to smaller scales, it's that the strain gradients that you can achieve grow as you go thinner. Yeah? Okay. So this is more or less the summary of the physics that you absolutely need to know of flexoelectricity. That it's allowed both in insulating and semiconducting materials and irrespective of whether your material is sensor-symmetric or not, so it is quite universal. And it is the strain gradient that allows you to extract polarization even in sensor-symmetric materials. That is proportional to dielectric constant, and therefore it will generally be big in materials with big dielectric constants, so ferroelectrics. And that its effects will be most dramatic at the nanoscale, purely because you can get bigger strain gradients. Right? This thing is done in the world. Okay. Any questions before I move on to the next stage?
You have on some slides the coefficient as F and on some slides as U. Are they the same?
They are not the same, and I will explain the difference shortly. Yeah.
In one of the slides, you shown that as temperature changes, there is
Yes.
change in the flexoelectricity.
Mm-hmm.
But when it goes up, does it follow the same same points, or does it have any distresses also? In one of the cases, like
So basically, as far as we can tell, flexoelectricity tracks exactly the dielectric constant. So whatever your dielectric constant does as a function of temperature is what your flexoelectricity will do as a function of temperature. Now, if you divide the flexoelectric coefficient by the dielectric constant, you get F, which is what he was asking, and F should be more or less temperature independent.
It's maybe a very stupid question, but why isn't it possible in metals?
It's not a stupid question. I asked myself that question and I even tried to measure it. So maybe it's a stupid question that I was stupid enough to try. I think the answer is you may be able to induce a polarization by bending in a metal, but you won't be able to measure it. Because remember the way in which we measure polarization? Let me see if I can find it. Is I induce, or let me see, maybe it's even better now. Let me go to here. So when I bend this, it will polarize. As it polarizes, you need to compensate that polarization by creating, by generating a displacement current that will flow through your amperimeter, and that's when you will measure your amperimeter. However, if your material is metallic, the displacement current is going to flow through the metal rather than through the amperimeter. This is a much shorter path than here. So maybe I am polarizing my material, but I just can't measure it. So this is not to say it doesn't exist. Maybe metals can be flexoelectric. I think from a symmetry point of view, they should be. I just don't know how to measure it yet.
Can I make a comment?
Please.
So from my point of view, the static polarization is just never well defined in a metal. Maybe on some time scale you can cause currents to flow that aren't completely screened. So I think, maybe in a dynamic measurement you can measure something like it, but I think at the static limit, never.
I guess what one might be able to measure is the loss of centrosymmetry at the lattice level.
Absolutely,
And
yes.
whether you can call that polarization or not, it's a different question. Anything else? Okay, so how big is flexoelectricity? This question is not trivial, and I dedicated quite a few years of my life to trying to answer it, because flexoelectricity has an intrinsic contribution, but on top of this intrinsic contribution, there's another contribution which is surface piezoelectricity, which is not exactly intrinsic, but it's always there. So in a sense, it's inherent. You can never get rid of surface piezoelectricity. You can also have piezoelectric artifacts if your material has polar nanoregions, or has a gradient of defects or whatever. And finally, if your material is semiconductor, you can also have some free charge contributions. And all of those can change enormously your flexoelectric coefficient.
Maybe it's a bit of a question about piezoelectric measurement. Let's say if I'm measuring ET1 coefficient using 4-point bending, in such case, it can be assumed as an artifact some point of time, or I'm also measuring the flexoelectric effect.
Well, if your material, if your piezoelectric was perfectly homogeneous, and you're measuring in a perfect 4-point bending geometry, then you should measure no piezoelectricity, because the compression on one side excitedly cancels the extension on the other side, and so you shouldn't. As I shall see, yes, I will try to show you later, even the smallest deviation from a perfectly homogeneous distribution of piezoelectricity will give you a flexoelectric-like signal, and that is due to piezoelectricity. Yes? But yeah, in theory, perfect piezoelectric under perfect bending will not give you piezoelectric polarization and should only give you flexoelectric polarization. Yeah? Okay. Okay, let's go through this. How big is flexoelectricity? This was a first step that we did with Jawan Hong before he went to David Vanderbilt's group and learned how to do this properly. This was our first step at trying to measure, quantify, estimate flexoelectricity from a first principles point of view. And this is inherently difficult because any of you who knows anything about DFT would know that usually you assume a periodic boundary condition. You make an infinite crystal by assuming that the lattice on the left, you match it with the lattice on the right, and you can make an infinite crystal from a very small unit cell just by repeating. But of course, a strain gradient breaks the periodic boundary condition, right? If I have something compressed here and something extended there, I cannot now take this unit cell and put it here because they don't match. So our trick to do that was to do like an accordion shape unit cell that would be, say, extended here, compressed at the bottom, and extended here again, and then match this to this, and then the two would fit. And here I have a strain gradient, and I would look at the polarization here. This is a bit dodgy because basically, in order to induce this strain gradient, I have to clamp the position of some atoms and let the other ones relax. And which atoms I clamp and which atoms I let relax is a random choice. Okay, so it's not perfect. Nevertheless, this trick gave us a reasonable number for the flexoelectric coefficient of SVO, which was of the order of a few nanocoulombs per meter. which matches the order of magnitude of our experiment. And I should also emphasize that when it comes to flexoelectricity, order of magnitude agreement is as good as it gets. Okay? Even within experiments, if you take two different single crystals, you will get variations of factors of 2 or 3. Okay? That's acceptable. I mean, it's what it is. When we did exactly the same trick for the BTO, however, we also got nanocoulombs per meter, and yet the experimental flexoelectric coefficient of BTO is not nanocoulombs per meter, it's microcoulombs per meter. So we had a 3 or 4 orders of magnitude disagreement between theory and experiment. And we needed to understand that. Okay, and the first thing that we thought is, okay, DFT is usually calculated at 0 Kelvin. Everything is perfect, there's no defects, and everything is at 0 Kelvin. But we know that flexoelectricity is proportional to dielectric constant, and dielectric constant is proportional to temperature, or it changes with temperature. So the first thing to do a proper comparison is to get rid of the temperature dependence, and we do so by dividing over the dielectric susceptibility. And that's the F coefficient that you asked about before. So this is the flexoelectric coefficient that you measure experimentally. This is the same thing divided by the dielectric constant. We get F. Okay? We call that F. Some people call this the flexocoupling coefficient. Some people call it the flexovoltage coefficient. We haven't agreed yet on which is the best word. We can make a poll later. Okay, and if you do that for BTO, you see the following. So the flexocoupling coefficient F, which is a flexoelectricity divided by the dielectric constant, indeed in the paraelectric phase is quite constant, quite flat. You can see 10 volts. Depending on the orientation of the crystal, you see some difference, but it's still flat. Then, below a certain temperature, you start getting some hysteresis and some temperature dependence. These we interpret as being a signature of the presence of polar nanoregions, which, and the amount of polar nanoregions depends on whether you're on cooling or on heating. And then at low temperature, the thing jumps, goes through the roof, and it becomes enormous. Here, we are certain that this is due to piezoelectricity. Okay. So here, we are already in the low temperature state of BTO, which is ferroelectric, and therefore also piezoelectric. So we think that this enormous flexocoupling coefficient is not real, it's piezoelectricity. You were asking about that earlier. This, however, looks very much like what it should be. So there's some phenomenological calculations that Tagansev did a while ago, and he expected that the flexocoupling coefficient should never be a number much bigger than about 10 volts, and indeed for BTO it's not much bigger than about 10 volts. So anything that is bigger than this is coming from extrinsic contributions, polar nanoregions being one, piezoelectricity being another, but also you can see that there's a strong orientation dependence of this flexocoupling coefficient. And that's not completely trivial because the material is cubic. Also, you may observe that at very high temperatures, the apparent flexocoupling coefficient starts to go up again. It's no longer flat, it starts to go up. Okay, and we think that this has to do with a free charge contribution. I will get to that later. Okay, but the intrinsic one is of the order of 10 volts. And in fact, we have measured a bunch of oxides. Here I've only listed the peroxides, but I think even for titanium dioxide, this is also the case, that when you look at the intrinsic part, the one that is temperature independent, beyond any hysteresis, whatever, it's always a number of the order of about 10 volts. Okay, so the smallest we've measured is about 5 volts, and the biggest we've measured is about 30 volts. Yeah. So if you have a material for which you expect that there will be flexoelectric effects, and you have no idea as to how to quantify them, your first guess, or my first guess, would be 10 volts times the dielectric constant. Okay? And that will probably give you a good approximation. So if you don't know what's the flexoelectricity of your material, that guess for me would be quite acceptable. 10 volts times the dielectric susceptibility. Okay. I've mentioned earlier that if you have an inhomogeneous, so if something is if you have a material that is piezoelectric and perfectly homogeneous and you bend it, there is no net deformation because the extension on one side cancels the compression on the other, so you should not expect any piezoelectricity. But if the distribution, if your material is not perfectly homogeneous. So say it's a little bit more piezoelectric at the top surface than at the bottom, and that is quite often the case because you have gradients of defects, for example. Then when you bend it, you will measure an effective flexoelectric coefficient that is basically proportional, well, it is the integral of the distribution of piezoelectricity. Okay, basically it's proportional to the asymmetry in the distribution of piezoelectricity. That sounds all very abstract, but what it boils down to, if you want to put numbers, is if you take very tiny or PZT and you have a 1 millimeter crystal and try to bend it, which is what we typically do in our DMA experiments, if you have just a 0.2% difference between the polarization at the top surface and the polarization at the bottom surface, that is enough to give you an effective fake flexoelectric coefficient of the order of microcoulombs per meter. So already 1,000 times bigger than what we would measure in STO. Okay? If your material, what it boils down to is, if your material is ferroelectric or piezoelectric, you have no hope of measuring the intrinsic flexoelectric coefficient in the polar phase. Yeah? Is that clear? Did I go too fast through this?
Is there a link between ferroelectricity of the material or even piezoelectricity of the material and flexoelectricity? I mean, is there a direct correlation or not?
Well, there is, for a starter, a correlation via dielectric constant. So any material that is highly polarizable, for a material that is highly polarizable, it will be easy to become ferroelectric, and it will also become easy to be, to give you a big flexoelectricity. Both things are a manifestation of the polarizability of a material. That's as regards ferroelectrics. There isn't, however, as far as I know, a direct causal relationship between something having a large flexoelectricity and it being ferroelectric. It's just that both things derive from the same polarizability of the lattice. For antiferroelectrics, there used to be a theory that I don't know. Okay, there used to be a theory which said that an antiferroelectric is essentially a material that has built-in polarization gradients. You can think of a piezoelectric as, an antiferroelectric as something that is changing polarization every other unit cell. So that's as big a polarization gradient as you can think of. So the theory went that if this thing has such large built-in polarization gradients, it's because it likes to have gradients. So perhaps the Landau theory is, perhaps the thermodynamic potential will have a large flexoelectric contribution that is negative, so whereby when you have a gradient, you lower the energy of your material. That was the theory. So far we've measured a couple of antiferroelectrics, and I am very disappointed to say that the flexoelectric coefficient was not very large at all. So whether the theory is correct or not, experimentally we have no evidence for it. But the concept, the concept sounds nice. I would like to believe that it's true. It's just, so far it doesn't seem to be. Yeah? Okay. So I mentioned intrinsic flexoelectricity, then fake flexoelectricity that comes from piezoelectric contributions. There's another piezoelectric contribution that is not fake. This one really is there all the time, and it goes like so. If you have any material, even a perfectly centrosymmetric material, the surface of the material is necessarily piezoelectric, okay? In the sense that it's not centrosymmetric. What you have above the surface is different from what you have below the surface. Therefore, it's not centrosymmetric, and therefore it's piezoelectric. Okay, and the piezoelectric coefficient of the surface, let's say, points, let's say, in this direction here, and it points in exactly the opposite direction on the other surface. Now, if I take this crystal and I stretch it or compress it homogeneously, the change in polarization, the piezoelectric change in polarization here, is identical and of the opposite sign as the piezoelectric change of polarization here. Okay, so the two surface, what I'm saying is that two surface polarizations cancel each other, and you will not measure anything. However, if I take the same crystal with the same surface piezoelectricity and I bend it, now here I am extending, here I am compressing, which means that the strains that I am applying are of opposite signs. So now the two contributions that were previously opposite to each other now if you apply a strain of the opposite sign to something that is opposite, what you get is two polarizations that point in the same direction. Okay? Therefore, when you bend your crystal, you will get a surface piezoelectricity, a net surface piezoelectricity that comes just from the surface. And that's ignoring the fact that your material is flexoelectric. Okay? Just from the surface. You bend any crystal, and the surface will give you a surface piezoelectric contribution. Now, this is a real killer, because you might think that surface piezoelectricity, or I used to think anyway, that surface piezoelectricity should be negligible for very thick crystals, but it's not so at all. And the reason why you can never neglect surface piezoelectricity is the following. Surface piezoelectricity, of course, is proportional to surface strain. For a given amount of curvature, how much strain you get on the surface depends on the thickness of the crystal. Okay, the thicker it is, the more strain I'm going to have on my surface when I bend it. So the surface piezoelectric contribution will increase proportionally to the thickness of the crystal. And even though the surface to volume ratio is decreasing linearly with thickness, the contribution from the surface is increasing linearly, which means that when you take the two effects into account, the surface piezoelectric contribution is independent of thickness. Okay? So the surface piezoelectricity is growing proportional to the thickness. The amount of surface compared to the volume is decreasing proportional to the thickness. One thing times the other means independence of thickness. Surface piezoelectricity does not depend on thickness. And this is very profound. Okay? Okay? It's so profound that so I think David mentioned Max Stengel. He's a theoretician who works in Barcelona on the theory of flexoelectricity. And he is the first one who told me that in theory, if you take a strontium titanium single crystal and you just change the surface termination from being TiO2 terminated to SRO terminated, so just the last atomic layer on your 1 millimeter thick single crystal, the sign of the total flexoelectric current should change. I found that absolutely outrageous. Okay? You have 1 millimeter thick crystal, you change just the last atom, and you change completely the sign of the polarization. I didn't believe him. Experimentally, I still haven't managed to prove whether he's right or not. But now I understand the physics, and I think the physics is solid. In fact, physics coming from Max, chances are that it's always going to be solid. That's a different thing. Okay, so it's independent of thickness. Moreover, when you try to polarize this, if you don't polarize that, then there's going to be a polar discontinuity. And you don't like that. You know, you want the displacement vector to be continuous across your crystal. So if you try to polarize this, the surface, the bulk will also try to polarize itself in order to keep a constant displacement vector. How much this polarizes depends on its dielectric constant. So the higher the dielectric constant of the bulk, the better you'll be able to screen this polar discontinuity, and so the bigger the net contribution from surface piezoelectricity. Which means that surface piezoelectricity is A, independent of thickness, and B, proportional to the dielectric constant. Exactly the same as bulk flexoelectricity. So the conclusion of all of this is that surface piezoelectricity is technically indistinguishable from bulk flexoelectricity. And again, it's a good argument to be made that since you cannot distinguish it even on a very fundamental level, maybe you shouldn't treat them as two different things. Max's belief is that basically they are two ingredients of the intrinsic flexoelectric coefficient. So the inherent flexoelectric coefficient has the inherent bulk contribution and the inherent surface contribution. This is true, but I have a small disagreement in that you can actually change the surface. You can change the surface, for example, by changing the orientation or by changing the termination. In the case of BTO, it's very clear. If we measure BTO with 3 different orientations, we see very different total flexoelectric effects when we shouldn't expect such large difference for a cubic system. So we think that this difference in the intrinsic regime is due to the different type of surface that we have due to the different orientation of the crystal. Is that clear?
What kind of piezo samples did you measure this on?
Single crystals.
Which size?
So they were about 1 millimeter thick, well, one centimeter square by 1 millimeter thickness.
Okay.
We got, well, the 1 millimeter thick ones tend to break easily, so we also bought some thinner ones, but yeah, typically between 200 microns and 1 millimeter thickness. It's an expensive experiment because VTO is very expensive, and inevitably we bend them to destruction. The other thing is when you heat things up, okay, when you're in the cubic phase, how does it go? Yeah, when you come from here, you're fine. When you're in the low temperature phase, VTO is ferroelectric and ferroelastic, which means that it has twin walls that allow you to accommodate the strain gradient. Basically, if you take a VTO crystal at low temperature and you try to bend it, you will bend a lot, purely because of the main walls allow you to do so. Of course, when you go into the paraelectric phase, the main walls are not there, but your crystal is super bent, and then that's when it will snap. So my advice, if you want to do this, is start in the cubic phase, where the bending is is what the lattice really can withstand, and you cool down. As you try to reheat again, it will break. Yeah. Yes, more questions?
So is it safe to assume that flexoelectricity could be one day used for high temperature operations to see some microelectronics?
It is my great hopes. Yeah. So far, as flexoelectricity, I think it's cool. And some people believe it's useful. So in fact, the first person who tried to do useful things with flexoelectricity was Eric Cross. He's now passed away in Penn State. He worked for the Naval Research Laboratory of Penn State, of the Navy. And his thinking was that flexoelectricity, well, basically that exactly what you say. Flexoelectricity, since it does not depend on the existence of ferroelectricity, which only exists below Tc, it exists at all temperatures, including the very hot temperatures that you can achieve in the head of a missile that is traveling through Earth. That makes me a bit sad if that is ever the first application of flexoelectricity, you know, to put pressure sensors in the head of a missile. But yes, in theory, that's one of the advantages. The other, of course, is that it exists in lead-free materials. So the best piezoelectric is PZT and similar things like PMMPT and all that, all of which has lead. Flexoelectricity exists in all materials, including, of course, lead-free ones. Yeah?
Regarding the surface piezoelectricity, if I take a surface which develops some polarization, I neutralize the polarization by putting some hydrogen on there or H minus or so, and then I start bending it.
Mm-hmm.
How much do you think you can reduce surface piezoelectricity in this way? Will it be completely or just a factor of?
That's a complicated question. So as you try to bend it, it will try to polarize. It will try to change its polarization because it's piezoelectric. How much it manages to switch polarization will depend on how efficiently you can screen that polarization. If you cannot screen it at all, because there's not enough absorbance in the atmosphere and or your dielectric crystal has a very low dielectric constant, then this surface piezoelectricity will be almost negligible. But if you have a lot of adsorbents that can go in and screen this polarization, then the polarization will develop. Now, whether you can measure it or not is different. But, the better you can screen, so the more adsorbents you have, in theory, the bigger the surface piezoelectricity that you can achieve.
Can I make another comment?
Please.
Just to give a different perspective on this. Since what you're talking about is basically the surface dipole layer.
Mm-hmm.
That's really the same thing as the work function of the surface. The difference between the electrostatic potential inside and the vacuum outside.
Mm-hmm.
And so the problem is that the work function of the surface depends on the strain. If you strain it, it changes, and that gives this. It's another way of looking at the same effect. So I guess one way of answering the question is, if you could somehow find some surface preparation that has the property that if you strain the surface, the work function doesn't change, then you would kind of get rid of this surface piezoelectric contribution.
Cool. Thank you.
I don't know how to do that.
In cubic system, you have 3 different coefficients for the tensor.
I think so, yes.
So, do it represent
No.
these different things?
No, it's a bit more subtle than that. Okay, so on the one hand, yes, you only have three different independent flexoelectric components: the longitudinal, the transverse, and the shear. The dielectric constant. Okay, so that's how many components you have. How those components change as a function of the orientation of the crystal. That has to do with some rotation transformation of the flexoelectric tensor. Now, if the flexoelectric tensor was the dielectric, the same as the dielectric constant, which is a two-rank tensor, this would be perfectly orthotropic, which means that these three things should be exactly identical. But it's not a two-rank tensor; it's a four-rank tensor, which means that it has no reason to be perfectly orthotropic. But you can quantify what is the maximum difference. Someone can, not me. Max Engel can, and he did. And the maximum difference that you should get between these three orientations is a good bit smaller than what we've measured, a lot smaller. Okay? But yeah, that's a good question. So, a priori, even though it's cubic, there's no reason to expect that the three orientations will have exactly the same flexoelectric coefficient. Good point.
Connecting to the same question, do you have a qualitative explanation why the 111 seems to have a less smaller coefficient than the 111?
No, and in fact it's exactly the opposite of what I expected. Because if you're familiar with the perovskite, I think I know where you're going. So if you're familiar with the perovskite unit cell, the 001 planes are charge neutral. Okay, either titanium dioxide or strontium oxide, thinking of STO, are charge neutral, have charge 0. Either of these two will not be charge neutral. It has a lot of charge, the last surface termination. So I expected that if you had a surface that is very charged, it will also be very surface piezoelectric. Experimentally, that doesn't seem to be the case. On the other hand, I have no idea of what's the termination of my crystals. It may well be the case that even though a perfect surface termination would be very charged, the termination of my crystal is not homogeneous precisely because that charge probably costs a lot of energy. Maybe I have a combination of terminations that gives me 0 overall. I have no idea. Yeah?
How do you measure such a big drop in voltage? What instrument is it?
Just a lock-in amplifier. Yeah, and I don't measure, okay, this is a bit misleading. I don't measure voltage, I measure current. I measure the displacement current. Displacement current multiplied by the frequency is the charge, which divided by the area is the polarization, which divided by the strain gradient is the flexoelectric coefficient. And that, divided by the dielectric constant, which I measure separately, is the flexocoupling. Okay, so I don't measure directly voltage, I measure current. After a bit of translation, I convert that into flexoelectric coefficient, and then I convert that flexoelectric coefficient, which is measured in coulombs per meter or nanocoulombs per meter. I divide by the permittivity, and I get something that is quoted in volts, but I am not measuring directly a voltage. Typical currents that I measure are of the order of nanocoulombs. So if you take a single crystal of BTO, you bend it, the amount of bending that you can have, and given the size of typical crystals that you can buy, you measure currents between picocoulombs and nanocoulombs. If you are very lucky, or if you measure semiconductors, and I will get to that in a minute if I can, you can measure bigger currents of the order of microcoulombs. But that's kind of the order of magnitude in which we operate, and we measure it by a lock-in amplifier. Okay? I mean, it's not a big effect at the macro scale. The thing is, once you know the size of the coefficient, then you can extrapolate to what you multiply the flexo voltage coefficient times the strain gradient, and you know what this can do for you at the nanoscale. And this is where things get really exciting. Okay, so we quantify the coefficient at the macro scale, but we measure the consequences of it at the nanoscale. Yes? Okay, and there's another additional contribution to flexoelectricity which you can have in semiconductors, and that contribution comes from free charge. And if you remember, in fact, you don't even need to remember, you can see, if you look at barium titanate, the flexoelectric coefficient this time as a function of temperature more or less it follows dielectric constant. You have a bump here, this has to do with polar nanoregions, here you're more or less in the intrinsic regime, and then it starts to go up. And this starting to go up very much coincides with an increase in leakage in our sample. So we thought, okay, this probably comes from leakage. Let's see how far can we push it. Let's make our BTO super leaky. Okay, you can make it very leaky by putting it in a reducing atmosphere, taking oxygen out. If you take oxygen out, it will become oxygen deficient, obviously, and it will become visibly darker, bluish. Okay. With if you do this with STO, it can become almost black. Okay, so now it's more conducting, and if you now measure the flexoelectricity of this conducting BTO, oxygen deficient BTO, you see a huge effect. Okay, thousands of times bigger than what you see in the insulating case. And we need to understand this. Okay. If you remember my talk from 2 days ago, if you have something that is not a perfect insulator, you might also see, it might give you a giant capacitance. Remember the Maxwell-Wagner effect, barrier layer capacitor thing? So indeed what we see is if you take the BTO insulating, this is the capacitance that you measure, take the same single crystal and measure the capacitance, and it's also a lot bigger. Okay? So the way in which effective flexoelectric coefficient is behaving is very much like the way in which the effective dielectric constant is behaving. It's not the real dielectric constant, it's really the capacitance. Okay? Okay. That's important to understand what's happening here. So what's happening here is the following. If you take BTO and you try to bend it, basically you can think of BTO as being 3 capacitors in series, the interface being one of the elements, the bulk being the other one, and the other interface being the other one. Okay? You can measure the capacitance of this, and mostly the capacitance of this will be dominated by the bulk. Okay? Because it's 1 over the capacitance. It's 3 capacitors in series. The thing with the smallest capacitance, which is the thickest element, dominates. And likewise, when you try to bend it, you get the bulk flexoelectricity, you have a surface piezoelectricity, and these 3 things, these 2 things more or less, 3 things because there's 3 elements, more or less will try to match each other because we want to have a constant displacement vector. Right. If I now take the bulk away, I turn it into basically something metallic, something conducting, something that gives me as much free charge as I need, then it's as if this no longer existed. Okay, this dielectric element no longer exists because it's conducting. The interface may still be insulating because basically you have a barrier layer, a Schottky contact between a metal and your semiconductor. Okay, so let's assume that the surface is still insulating. So your effective capacitor is now only the interface region. And because the interface region is very thin, the capacitance is very big. That explains the Maxwell-Wagner effect. That's what I explained 2 days ago. But also, and that's important, when the surface piezoelectricity, so when the surface piezoelectricity tries to polarize, so you are stretching the surface here, you're compressing it here, the surface is trying to polarize. Now it can do so very cheaply because there's a lot of free charge that can screen the polar discontinuity. So whereas here the polar discontinuity imposed some limit as to how big could the surface piezoelectric polarization be, now there is that limit is no longer there. The surface piezoelectric contribution can be as big as it needs to be. Okay? So here, in the bulk, in the insulating case, surface piezoelectricity is limited by the dielectric constant of your bulk. Here it's not limited because in effect it's as if the bulk had an infinite dielectric constant. It has an infinite ability to screen the polar discontinuity, so the surface piezoelectricity can be as big as it wants. It's a bit subtle, but hopefully you get it. If you don't, ask me. And so that's more or less what's happening. And so now the surface piezoelectric contribution can be as big as I said, as it needs to be. And what you will find is that the effective flexoelectric coefficient is something that is proportional to the piezoelectric coefficient of the surface times the thickness. So this flexoelectricity of semiconductors should scale proportional to the thickness of your sample. And in that sense, it's not a true, it's not a constant because it depends on the thickness of your sample, but it can be big at the macro scale, right? Because this scale is proportional to the thickness. So whereas normal flexoelectricity is really only important when you go to smaller sizes. Semiconductor flexoelectricity is most obvious and manifests itself more strongly at the macro scale, which I think is kind of cool. Yeah? No questions? Okay, so this is just what I was saying. If you take, okay, we did that initially with BTO, oxygen diffusion. We also took our favorite titanium dioxide crystal. That was the flexoelectric coefficient in the insulating case. That's nanocoulombs per meter. Then we bought a niobium-doped titanium dioxide, and we measured the flexoelectric coefficient, and it was a deal of microcoulombs per meter, so thousands of times bigger. And indeed, for this semiconductor flexoelectric material, the coefficients scale with things. It's not a perfect linear scaling. I guess nature is not perfect, or our lab is not perfect, but you see a proportionality. Yeah? Okay, so that brings me to the end of part 2. Take-home lessons. The intrinsic flexocoupling coefficient is always of the order of about 10 volts. So the intrinsic flexoelectric coefficient of your material will normally be 10 volts times its dielectric constant. That's lesson 1. Lesson 2 is if your material has any form of piezoelectricity, so polar nano regions, or basically, or if you are in a piezoelectric state, then you can have very strong additional contributions coming from this parasitic piezoelectricity. And then there's also surface piezoelectricity. This is always there, always. And in semiconductors, in fact, that is the very dominant effect. In fact, it's the only effect, or the only effect that you can measure. Yeah?
Has the same been done for STO, like where you make oxygen vacancies to make it more conducting in the center?
I have not done it, but there's no reason why it shouldn't work. In theory, yeah, you can just put it in the oven and see what happens. I mean, if it works for niobium-doped rutile, it should work for niobium-doped STO, and certainly for oxygen deficient STO as well. You should be careful that you don't push it too far into the metallic phase, because once it's metallic, then you cannot measure it, right? So it's, for this semiconductor effect, it is essential that the barrier layer, that the Schottky contact, that there is something a bit insulating in your sample, in between the electrode and the bulk, and the conductive bulk. There has to be a sufficiently insulating layer, the polarization of which is what you actually measure. If your material is completely metallic, then you don't have this insulating region, and so you don't measure any polarization.
In that sense, you can just deposit normal STO on top of the niobium-doped STO. Okay.
I don't know whether that would work. Don't know whether that would work. If you think about it. Because if you just put it, so, okay, yeah. The last layer of the STO that you've deposited would give you this surface piezoelectric contribution, yeah. Yeah? Oh, no, for time. All right. No questions yet? No more questions for this. Right, so now let's go for the kind of cool, or I think cool phenomenology that you can, the kind of things that happen when flexoelectricity takes place. Right. Right. The very first application that people thought of for flexoelectricity was as a substitution for piezoelectricity. So we've just mentioned the temperature dependence of the piezoelectric coefficient in BTO or in PZT, also the fact that the best piezoelectrics contain lead. So the obvious first thing to try is, okay, can we use flexoelectricity instead of piezoelectricity to achieve a piezoelectric-like performance? And the trick is the following. What you do is you take your non-piezoelectric material and you engineer not the composition but the shape. Okay? And as long as the shape of your material is asymmetric, when you apply a force to your material, the stress will be asymmetrically distributed. Okay? So here, the force because this area is much smaller than this area, the force per unit area, i.e. the pressure here, is much bigger than the pressure here. So you have a pressure gradient, which means that you have a strain gradient. Things will be more stressed here than here. and if you have strain gradient, you have a polarization. Okay? So I apply a force to my asymmetric truncated pyramid, and I measure a polarization, and if I divide that polarization by the force, that is the definition of the effective piezoelectric coefficient. And you can measure it. Okay, so that was done by the group of Eric Cross in Penn State, and they saw that it was sizable, so they did this experiment with baryons strontium titled in the paraelectric phase, paraelectric but still with some parasitic piezoelectric contributions, and that's why it has such an enormous flexoelectric coefficient. But that's irrelevant. The point is, he used a material that is non-piezoelectric, shaped it like so, and compressed it and measured an effective piezoelectric coefficient. Moreover, as I told you, this thing is inversely proportional to size. He took the same truncated pyramids and made them half as big, and the effective piezoelectric coefficient, as you saw, was twice as big. Okay, so maybe you can read this, but this corresponds to 100 micron pyramids, and this corresponds to 50 micron pyramids. Yeah? That was a real experiment. This is not a real experiment, but a concept that Eric also proposed, which is instead of making these truncated pyramid things, you can make a flexural composite. The idea being that the transverse flexoelectric coefficient is often bigger than the longitudinal flexoelectric coefficient. So he expected this to give you much bigger performance than that. I believe this may have been the last thing he did before he died. So pretty cool. Right. So that's for sensors, something that converts pressure into electricity. You can do the opposite. You can do actuators. So a piezoelectric actuator, a BIMOF actuator, basically takes piezoelectric material, you attach it to something that is not piezoelectric, you apply a voltage, this thing is trying to compress, this thing cannot compress, or there's no wall to compress because it's not piezoelectric. So there's a tension between this temperature and this not letting it, and this creates a stress gradient whereby the thing bends. Okay, so on average this is more compressed than this is. Yeah? So way to compress what would otherwise be homogeneous compression into bending. That's how BIMOF actuators work. If you have a flexoelectric, you don't need the passive layer, you just apply a voltage and the thing will bend. Remember, however, that how much it bends goes as 1 over the cube of the thickness, so this concept will only be really useful, not for normal actuators, but for MEMS, so for things that are really thin. So micro electromechanical actuators or nano electromechanical actuators. If you do your thing micro or nano, the amount of bending that you can measure though is big, right? So this is the displacement on one of our STO membranes, and you can see it's pretty huge. And when you compare the flexoelectric performance of this STO flexoelectric actuator with the performance of piezoelectric BIMOF actuators, you can say it's in the mix. Okay, it's competitive. It's not the record. It's not as high as these things would be, but it's big. And in theory, if you could make this, a bit thinner, we should jump up because this goes as 1 over the cube of the thickness. We haven't managed to make it thinner, so we haven't beaten the record. But somebody wants to try, it's a good challenge. And finally, this is something else. This is not my work. This is work done by the group of Marin Alexei in Warwick. And this is a really, really cool piece of work. If you remember when I was talking about the bulk photovoltaic effect, you have a material that is polar, non-centrosymmetric, and you shine light on it, the asymmetry of the lattice separates the charge carriers and gives you a current or a photovoltage. And that's called the bulk photovoltaic effect. That only exists in materials that are non-centrosymmetric. But of course you can also break centrosymmetry, or you can also break symmetry by a strain gradient. And that's what Marin Alexei and Ming Yang have done. He took an AFM tip, he pushed with the tip of the AFM on the crystal. Under the tip of the AFM you break the symmetry, and so when you shine light, a photocurrent appears. And how much photocurrent you get is proportional to how hard you're pushing on the surface. So they attribute this to a flexoelectric effect. Basically, flexoelectricity turns your material effectively into a polar material, whereby the bulk photovoltaic effect can exist. And this was done with insulators. I would like to see what happens if you do that with semiconductors, because I think it will be a little more dramatic. Right? So the three applications that I've just mentioned are ways in which you try to use non-piezoelectric materials to achieve the same things that you would normally achieve in piezoelectric materials. So flexoelectricity as a substitute for piezoelectricity. The things get even more interesting if you use flexoelectricity in combination with piezoelectricity, because the two things can coexist. They are not mutually exclusive, and in fact, flexoelectricity is biggest in ferroelectric materials. So in ferroelectric materials, the two things can coexist, and if you go to small enough scales where flexoelectricity can be big, not only they coexist, but they can compete or cooperate with each other. And that brings in new functionalities that you would not have with only flexoelectricity or with only piezoelectricity. So this is where new physics can happen. Okay, so one thing that you can do, for example, is if you have our bimorph actuator, remember the bimorph piezoelectric actuator, and you look at the bending as a function of voltage, assuming that this is perfectly ferroelectric and there's only a ferroelectric contribution, so basically you see that the bending is proportional to the polarization. If you switch the polarization, you also get the same amount of bending. You get what's called a butterfly loop. If you look at the strain versus voltage response on a ferroelectric, this is what you get. Okay, butterfly loop, symmetric. The flexoelectric bending, however, is not symmetric. It depends linearly on the voltage. So if the voltage is, let's say, if the voltage is positive, the bending will be down, and if the voltage is negative, the bending will be up. Yeah? If you add this plus this, then you should observe a completely new, qualitatively new shape of the strain versus voltage, which behaves like a diode. Okay? A lot of bending for one polarity and no bending by the other. Okay, that's the idea. This would be what one might call a flexoelectric, no, a strain diode. Okay, so that's one of the things that you can do. I'm not going to show you the results because even though the result, even though the effect was there, we didn't achieve the perfect diode, and that's not so pretty. Okay, let's see what more interesting things that you can do. Okay, this equation looks quite horrible, but actually it's not. It should look a bit familiar to you. This is the Landau potential of a normal ferroelectric. You have the P squared term, the P4 term, the coupling to stress, okay? And then you can add the coupling to the strain gradient. So the strain gradient or polarization gradient. This would be the direct effect, this would be the converse effect. In fact, the two effects are the same. I could have put these two as one single coefficient. You can minimize this, and you can get the equation of state of your ferroelectric in the presence of either an electric field or a strain gradient. Yeah? And what you can see immediately is that anything that I can do to the polarization using an electric field, I can also do it to the polarization using a strain gradient. Okay, now F here is a flexo voltage coefficient, which is, remember, of the order of about 10 volts. This is the strain gradient, which at the nanoscale is about this number. So this effective flexoelectric field, this thing that behaves like an electric field, is a number of the order of between 100 and a million volts per centimeter. Okay? Big. A million volts per centimeter is big, by definition of million, right? In fact, it's bigger, can be bigger than the coercive field of your ferroelectric material. Which means that you can use strain gradient to switch the polarization. Now remember what I said at the very beginning of my talk, the shape and size of the unit cell for the up state and for the down state are identical. So if I apply homogeneous pressure to a ferroelectric, I will never be able to switch it by pure pressure. But if instead of pressure I apply a pressure gradient, a strain gradient, now I can switch the polarization. Okay? And this is exemplified here with the free energy. This is the free energy of bulk BTO. This is the free energy of BTO with homogeneous compression. It's still symmetric, so there's no reason to switch from one side to the other. If instead of homogeneous stress I put inhomogeneous stress, a strain gradient, then if I had been on this polar state, the strain gradient will make me switch to that state. And experimentally, you can do this by taking your BTO thin film with polarization up, you push with the tip of an AFM. Doesn't even need to be metallic. You don't connect it to a voltage because the whole idea is that you want to do it without a voltage. and you can achieve some voltage-free switching. Okay. So this is for writing, polarization. Obviously, the next thing that you want to see is, can we also read the polarization by flexoelectric means? And the answer, of course, is we can. And the reason why we can, we think, is the following. If you take any material and you try to induce some deformation, the energy cost of the deformation is Hooke's law. It's something that is proportional to the elastic constant times the square of the deformation. If your material polarizes when you try to deform it, you also have to pay an electrostatic cost, which is proportional to p squared, to the square of the polarization. Basically, this is the depolarizing field. Okay, so if you take a piezoelectric and you try to put some deformation on it, if you have no electrodes, you will see that it's actually more rigid than if it has electrodes and the two electrodes are connected. That's something quite funky, right? So the stiffness of your material does depend on how much polarization you create and how well you screen it. But it does not depend on the orientation. I can take the same piezoelectric crystal that was pointing like that, and I turn it upside down, and of course, the Young's modulus is not going to change. It does not depend on polarity. And this is basically because the stress, the strain, the elastic constant, everything here is given by even parity tensors. So tensors that do not change under space inversion. But if you have flexoelectricity, so if your deformation is inhomogeneous, then your ferroelectric material will have two sources of polarization when you deform it. One given by the piezoelectricity, and that depends on the orientation, okay, it depends on the polarity of your ferroelectric, and one given by the flexoelectricity, and this only depends on the direction of the strain gradient. It does not depend on the polarity of your ferroelectric. That means that these two contributions can be additional to each other or subtractive from each other, which means that the total polarization can be big or small depending on the ferroelectric orientation, and so p squared will also be big or small. So I have not changed the sign, but I have changed the magnitude of the total polarization and therefore the energy cost of the formation. Yeah? I mean, siesta time, it's a lot of physics to take in 1 second, but...
I have a question about the typewriter kind of thing. So you switch it, in this case, without applying a voltage?
Yes.
To be able to switch it back when you do apply the voltage?
I would be able to switch it back by applying a voltage, but then it wouldn't be a voltage-free operation.
Yeah, okay, but then you could do sort of a read.
Yeah, so I can delete that by applying voltage or by picking, but by pressure, because I can only push from one side, I can only write in one direction. And that's why it's like a typewriter.
Yeah.
Most people here are too young to have seen a typewriter in their lives. But when I was young, they existed. And it's like a typewriter in that you type, once it's typed on the paper, the only way in which you can remove is by using T-Pex, which was an extremely toxic thing, chemical white paste that you would put on top of that. So you would erase by chemical means. So the way of writing and the way of deleting were not symmetrical. So conceptually, it's very much like a typewriter. As such, by itself, I don't think it's a sufficiently good technology. We need to be able to write voltage-free and rewrite voltage-free, and ideally also read voltage-free. Okay, and we're working on ways to do this.
So this is a symmetric force that you never apply, right? You have one center and it basically spreads out. So the gradient, I mean?
Yes. Okay, well, the force is symmetric, so otherwise my crystal would run away from me, right? The acceleration, so the force that I'm applying is counteracted by the table under my sample. But the stress distribution is asymmetric.
Yeah, okay.
And this is the thing, you need a strain gradient. Yeah. So the force.
Yeah, sure.
Yeah?
Yeah. Within the film, right?
Yes, yes.
Yeah. Okay.
Yeah. So there's a lot of strain here. There will be, okay, imagine this was a 3D thing. There's a lot of strain and deformation here. There's not so much strain and deformation here because the stress has been kind of radially dispersed into the film. So here there's almost no stress. And this stress gradient, usually strain gradient.
Yeah, I understand. I was more wondering if there's maybe a way to apply something which doesn't have a center, but it doesn't.
I think the way to do this is not to do in-plane, so not to do out-of-plane polarization, but to do in-plane polarization. So if you have something that is in-plane polarized, I can drag my tip towards the right, or drag my tip towards the left, and so that flexoelectric writing will write the polarization in plane that way or that way. That way you make it reversible.
Yeah.
Yeah? Okay. So this is, hopefully, if you are sufficiently awake, you will understand, or at least believe, that the cost of the formation does depend on the polarity of your ferroelectric. Because the piezoelectric polarization can be additional to or subtracted from the flexoelectric polarization. You can measure this effect by doing indentation. We have, and indeed it is asymmetric. We will not go into the details. So if you take a periodically poled lithium niobate crystal and you indent on, these are the up polarized domains, or you indent on the down polarized domains, maybe you cannot see them, but trust me, there's a hole here done by the indenter. You see that the contact stiffness is different, right? It's pretty cool. It means that we've read the polar state of our domains by punching a hole. This is a very definition of destructive readout because we are punching holes. Okay, but the stiffness is actually an elastic property, so we should be able to probe it without making holes, and we can do that by tickling the surface with the tip of an AFM. Okay, so you look for the resonance frequency of the AFM in contact with the surface, and depending on whether the polarization is up or down, you see a bigger resonance frequency or a smaller resonance frequency. The difference is not very big, but it's there.
On the top of your ferroelectric, you had the top electrode.
No, we had the electrode at the bottom.
So there was okay.
And this periodically poled lithium niobate, you buy it off the shelf. It's done with electrodes, but after it's been poled, the electrodes are removed, the thing is polished, and you have something with perfect parallel domains of up and down polarization. And then you go with the...
I guess for this you would have to measure both domains to figure out which one's which. Like you wouldn't be able to just measure one and say this is up, and then you need to compare it.
Okay, oh, exactly. Yeah. Here is what we've done. So we've scanned across the whole surface and we've seen how the resonance frequency changes from domain to domain, and we've done it on various domains. With indentation, I mean, here I want to, how they say it, praise Kumara, who's the PhD student, is a PhD student that did this. Anything that depends on fracture is a bit of a stochastic process, how much things break. There's certain statistics associated with this, so if you want to do this experiment well, you need to make a lot of holes. Okay, so and for each one of these holes, she had to then look in which domain it had fallen. So it's a very careful and patient piece of work. Okay. Another thing that is interesting about flexoelectricity is that, okay, it depends on strain gradients. The biggest strain gradient that you can have is a strain gradient that you would have in a crack, in a fracture. Okay, so if you have a crack propagating in your material, the tip of the crack is under as much stress as it can withstand. If you put any more stress, the crack will advance. Okay, so here you have as much stress as your material can withstand without breaking, and the actual contact point of the two sides of the crack is atomically small. So you have as much stress as you can concentrated in as small a volume as you can. So you have the biggest possible flexoelectric polarizations and flexoelectric fields in a crack. They are so big, those flexoelectric fields, that if this crack propagates in a polar material, in a ferroelectric, in this case lithium niobate, it can cause switching as it travels. Right? Of course, it will only cause switching if the flexoelectric field is anti-parallel to the polarization. The crack that propagates in the opposite direction will not cause any switching. So in this case, it did work. We did see a trail of switched flexoelectric domains in the wake of our crack. Sometimes it doesn't work, or you don't see them. We don't know if it's because there is back switching. We think it's because there is back switching. In any case, if one of the cracks is switching as it propagates, some of the crack energy is being dissipated in the form of ferroelectric switching, which means that the crack has less energy available to propagate. And therefore, the crack that propagates against the polarization doesn't go as far as the crack that travels in favor of the polarization, which means that fracture physics in polar materials is asymmetric. And this is, I think, also quite profound, because in mechanics you always assume that everything is centrosymmetric, because as I was saying, stress and strain, all these things are given by even particle tensors. Once you have strain gradients, you can no longer assume that, so you can never assume that your fracture pattern is going to be symmetric in a polar material. Whether this is useful or not remains to be seen. It does mean, though, that how much your ferroelectric ceramic fatigues or cracks depends on the polarity. So if you have an actuator that is fatiguing due to built-in stresses that are fracturing the material, we think that playing with the polarity of the actuator might mitigate the fatigue of the material. Okay. Let me emphasize, this is really profound, and it only is possible if you have the combination of flexoelectricity and piezoelectricity. If you had either effect alone, you would not see such asymmetry.
Would the change of polarization be at all
Sorry.
to do with the surface piezoelectric effect as well? Because like the crack would be making another surface from it.
Yes, I have no idea of how to account for the surface piezoelectric of the new surface that you are creating. It will be there. My first approach is to subsume that within the effective flexoelectric coefficient of the material. Yeah? 3 minutes left. Whoa, whoa. Okay, we'll talk about that. Bones, since we've talked about cracks, and I've said that bones are flexoelectric. They are not very flexoelectric. The actual flexoelectric coefficient of bones is not that big. But remember that in cracks you have very big strain gradients, so that small flexoelectric coefficient multiplied by the strain gradient of your bone is big enough to really affect the cells near the bone. Okay? And what I've drawn here, these two contours, are the isocontours of the known electric fields capable of electrocuting directly, electrocuting your sample, your cell, killing it, and the isocontour of the electric field that is known to be able to electrostimulate your bone cells. And these contour fields are the flexoelectric fields around the tip of a crack. So bottom line is, we think that flexoelectricity does play a role in the healing of your bones. It's the way in which your bone, when it has a fracture, tells the repair cells, come here, there's a problem. So besides all the functional curiosities and interesting physics of flexoelectricity, it may well be the case that it plays an important role for us. That's it. Game over. Right.